Hi everyone, before we start this class, I want to apologize that throughout recording the video, I wrote the momentum operator wrong. Okay, I wrote the momentum operator wrong. So before we proceed to the course video, I want to be very clear that the momentum operator here is h bar I partial x. Okay, if its momentum on the x direction. And if we use q to represent position, then the momentum operator is h bar I partial q. Or another way that you can say is minus I h bar partial q. Okay, and no matter what I wrote in the following 1 hour, probably 1 hour and 15 minutes. Please remember that this is the only correct form for momentum operator. Okay, I'm extremely embarrassed by my own mistake, but I want to make it very clear. Okay, at the beginning. Thank you. Hi everyone, welcome back. Today we're going to keep talking about how to quantize Maxwell equation, okay, into photon. And in the previous class, we've learned that, okay, in order to quantize this field, what we need to do is that we need to write down the energy of the EM wave, okay, inside a pair of mirror. And then we can define, okay, we can make some definition for the electrical wave amplitude. And then what will happen is that, okay, then you have A and have a Q. And when you write it in this form and also B, okay, because of Maxwell equation, you can derive B from E. And then okay, then you get this Hamiltonian, which look exactly like a harmonic oscillator, where you have potential energy and then you have kinetic energy, okay? And this step, okay, making the P, or, well, this one is actually mq dot, right? Mq dot velocity. And making the velocity into momentum and momentum into an operator, okay, is what we call quantization. Okay, quantization. And this is possible because in a mathematical sense, once your Hamiltonian, your energy is in the exactly same mathematical form, then there's no difference whether your Q represent position or your Q represent the amplitude of the wave. So then we arrive here, okay, we stopped here last time, and we say that, okay, then from this point, from this equation forward, then we can just use quantum mechanics. And most of you know this equation, that's the Schrodinger equation. So the and this one is the eigenstate equation for the Hamiltonian, and the Hamiltonian is the energy operator applied on the eigenstate will give you the energy of that state and the state itself, right? So this is eigenstate function, okay? And you can see that this is Hamiltonian is a second order differential equation, right? Partial q squared, right? So so one way, okay, to solve this problem is just to just plug in h in here and then try to solve the possible possible wave function and then the possible energy level. And this is exactly what people do this is exactly what people did first for the harmonic oscillator, okay? And we can kind of draw the solution here, and we're not going to go through them, okay? So suppose this is Q. This is what we called energy. Now let's see. This is VQ. VQ is kinetic is potential energy, which represents this term, right? So you see this. And if it's a harmonic oscillator, then you can think of it as the particle. Okay, the harmonic oscillator will be confined in this potential well, right? It's oscillating back and forth. And then if you have higher energy, then you can oscillate a lot. Your amplitude will be a lot larger. So if you really solve this equation, then what you will see, okay, solve this equation, you will see En is equal to h bar omega n plus 1/2. and then n equals 0, 1, 2, and keep going. Okay, keep going. And the function, okay, the function the eigenfunction you solve from here. By the way, this is called Dirac notation, the bracket. Okay, the right angle bracket. This is called Dirac notation. Writing this by itself actually doesn't mean anything. Later we'll show that you have to use left bracket and right bracket, and then create the inner product. And this notation start to make sense. Okay, so the wave function. Okay, if you check mathematical handbook, you can actually solve it. Although it's not very. To be honest with you, I never use this solution. So you don't have to remember this at all. And then I think last year what I did is that I assigned this as an alternative final. Is that final exam is that if you are willing to go through the trouble, okay, to solve this eigenstate step by step, then I can waive your final exam. But I mean, in this semester, I don't think that's necessary, because if you do your homework, then that's almost like you waive your exam. You already get 80% of the point. Okay. Okay, and h is a special function. It's called a Hermite polynomial. Okay. I think the time to do homework would be way less than try to solve this equation. Okay, and so if we plot this, what we will see is that for n equals 0, your wave function will look like this, psi 0. Okay, it's like centerized at it's like sitting in the center, and also it's even symmetry, which kind of makes sense. Okay, and then if you have n equals 2, then what you have is this. Okay, so you have so you have an off-symmetry, okay, function, and then so this is something that very, very common in differential equation and also in quantum mechanics, is that the fundamental, the lowest eigenstate with the lowest energy always, I think always only have one extreme value, like maximum or minimum. And then the second one, this is psi 1. And the second one will have 2 extreme values. And then the third one will have 3. Okay, and then based on that, you can change from even symmetry, off symmetry, even symmetry, if your potential energy here, has an even symmetry. Now, what this equation tells us is that the energy is quantized by h bar omega, right? By h bar omega. But of course, you will say, how do you really know that's photon, right? How do you really know that's photon? So, and also this entire solution is too complicated in a mathematical sense. It's almost like not useful to us. So what we're going to do here is we use something called second quantization, and then to derive all this result without serious mathematics. And this is really possible. And then it was, I remember, invented in the 1930s, by a physicist. And the result, I think, is really amazing. Okay. So in this second quantization, what we're going to do is that we're going to introduce a creation and annihilation operator that allow you to add photon and extract photon from the system. And I will try to introduce these operators in a relatively reasonable way. Okay. So now let's think about this question. If, right, it seems that if we accept the fact that h bar omega, what it means is that, okay, when you see the experiment, right, when you see the energy is equal to 2 h bar omega, you think of it as 2 photon arrive. If you see h bar omega, you think of it as 1 photon arrive. Then what you will see is that, okay, if I have, okay, a state that has n photon, right, n photon, is there a way to add the photon to the system, which just makes sense, right? In a laser, in anything, you can add a photon. That's kind of one of the, well, this is the thing that you kind of have to do. Otherwise, your system is like keep the photon number the same. And how about, right, if you have this, is it possible that you extract 1 photon? Right. The way to think about this is that, okay, if you have a beam of light hitting an atom, right, then this process represents that the atom emits 1 more photon, right, and this represents the atom absorbed 1 photon, right, so the number of photon reduced by 1. So all these are, very valid thinking, right, a very, very real situation that you might handle in calculation. So the question here is that, is there exist, okay, and then the other thing is that, okay, the carrying the wave function, okay, in all the calculation it's almost impossible, right, because it's too complicated. So the question is there an operator that we call it like lower operator, which if you act on n photon state, it will give you n minus 1 photon state. Right? If you can do that, then the calculation in quantum mechanics become very simple. When you say, okay, this atom absorbed a photon, right? Then what you do is actually you apply this operator on your state, and then they absorb a photon, right? Instead of going through all this ridiculous calculation. And the reverse process is, okay, is there a creation operator, right? When you apply to n photon state, it will add 1 photon to your system, right? So whether this operator exists and are they easy to use, that's actually the key question here. And if they exist and they're relatively easy to use, then you don't have to go through all this mathematics, okay? And ideally, you would think, okay, there might be some weird relation between annihilation and creation operator, okay? And the reason to think about that is because if you have a state that is n, right? You first add a photon, then you minus a photon. Then what it should do, it should give you the state itself, right? So what it means is that this operator seems to give you identity operator, right? If you multiply them together, it seems that it's just a number, applying to your wave function that doesn't really change your wave function, okay? So because of that, and if you think about it in linear algebra, okay, what type of operator can do this? Okay, there's a special type called unitary operator. What unitary operator does is that U times its complex conjugate or transpose conjugate, okay, is I. Okay, is I. So if you think, okay, if this is called unitary. Okay, so the logic is like this. If we can make the annihilation operator into a unitary operator, then it's a transpose conjugate of this operator would naturally, okay, give you creation operator, right? Because it has to create one and lower one to give you identity state, right? So if one of them is unitary, then the other one is its conjugate, transpose conjugate, right? So that way, okay, you don't have to carry two operators. You can only you only need to use one operator. Okay. Now let's try to guess what this creation and annihilation operator will look like. Okay, let's give you a symbol, right? Let's call it A. Okay, operator A. So the first thing, okay, we should know is that this operator has to be, from the En waves, function. You know that there are only two operators in the system. One is position, one is momentum, right? Or you can think about it, amplitude in electrical wave, amplitude in magnetic wave. So whatever this wave function is, whatever this creation and annihilation operator is, it has to be a function of Q and P. Right, it has to be a function of Q and P. Otherwise, there's no way that you can build a connection between your annihilation and creation operator with the system, with the photon. Okay, you're calculating here. So this is number one thing. Okay, and the second thing is that okay, what should it look like? Right, what should it look like? So the idea would be, okay, the simplest way of constructing an operator from two other operators would be this operator should be a linear combination should be a linear combination of Q and P, right? Of course, you can have like square root, you can have square. You can have higher order, but as an initial guess, okay, you must first try the linear combination first, okay, and then the third thing, right? We want to make this operator into a unitary operator. Unitary operator means that the complex, the conjugate transpose, okay, is not itself, right? Because this two has to be different so that when they multiply together, it give you I, right? The other way to think about it is if this is creation operator and this, if this annihilation operator, this must be different. Otherwise, you'll annihilate twice, right? So you will never get back to the original state, right? So in that sense, at least we know that A, okay, we want it to be unitary, okay, and then it's not Hermite. Hermite means an operator equals to its own conjugate transpose, or in other way we call it a joint operator. Okay, so not Hermite. And Hermitian operator, if you look at this, okay, what it tells you is actually very interesting. Okay, Hermitian operator tells you that you see the conjugate transpose. So you can think about, if you think about this as complex number, right? So the complex is its conjugate equals to itself, which means it's a real number, right? So of course, that's just an intuitive way to think about it. They are operators, so things are a little bit complicated. But what you can think of here is that, okay, A, if it satisfied Hermite condition, okay, the conjugate transpose equals to itself, then there has to be, then its eigenvalue shall have some special property, and in this case, the eigenvalue, if it's a Hermitian operator, is all real number, and that corresponds to measurable physics attribute. Okay, for example, X and P, they are all Hermitian. Okay, so here let's say Q and P are Hermitian. So you have Q okay. So if you have this, then what you will find is that okay, A dagger equals to alpha star Q dagger. Dagger means conjugate transpose, and then because alpha is a number, right? So you only have conjugate, you don't have transpose. P, right? So what it tells you is that alpha and beta, okay, is actually equal to this. And use the Hermitian condition for position and momentum operator. Okay, so what it tells you, okay, and this one cannot equal to A. So what it tells you is that if A dagger does not equal to A, then alpha and beta, one of them or both of them, has to be an imaginary number or has to be a complex number. Otherwise, if they are all real number, then A dagger will equal to A. Now let's use additional conditions to figure out, okay, what alpha and beta is most likely to be. Okay, so so here, okay, one thing that by looking at these operators, right, if you act A on a function, a wave function, it goes to another wave function, right? So in terms of dimension, right, in terms of dimension, A should be dimensionless. Right, it shouldn't change if you really move from one wave function to another wave function, right? It should be dimensionless so that you don't add any unit, okay, to the wave function. And to do that, okay, you have to normalize Q and P, right? Because Q and P, have different different dimension. This is position. This is momentum, right? So one way to do that is we know that okay. M omega square Q square, right, has a dimension of energy, right, has a dimension of energy, and energy has a dimension of h bar omega. So what you will have is you will have 1/2 and then M omega h bar square root of that Q, right, so you move this to that side, we'll have dimension 1, right? We'll have dimension 1. And similarly, you can do is you can have P square 2M has dimension h bar omega. If you move this to this side, then you will have goes to dimension 1. Okay, goes to dimension 1. Then the equation, okay, we can modify A a little bit now. A is now alpha, okay, a different alpha, and omega 2 h bar Q plus beta, okay, P, right? So then in this way, alpha, okay, and beta are just numbers, okay, are just numbers, so that A will be dimensionless. Now, what are the reasonable guess for alpha and beta? First of all, we know that in terms of energy, right, the kinetic energy and the potential energy, they are equivalent in this case, right? The maximum kinetic energy is the same as the maximum potential energy. So when it comes to here, okay, these two in this operator, it has to be equally weighted, right? Equally weighted. So alpha, beta, okay. The alpha and beta, their magnitude should be the same. And then for simplicity, we can let it to be 1, right? Because it really doesn't matter Okay, if there's a constant in the front of this operator, we can get rid of it, at the end. Now, and then, so if that's the case, then, it's very simple. We can just assume alpha is 1, right? We can assume alpha is 1 because, if you have alpha is minus 1 and beta is another number, you can always let that minus 1 be a constant in the front, right? Be a constant in the front, and then just add a number here. So it's not something that that is critical. Okay, so a guess would be, okay, alpha is 1, then beta, right? Because alpha is 1, beta is the same magnitude. Then, and also we know that alpha and beta cannot be all real, right? So beta has to be imaginary number. So let's say EI theta, right? Magnitude is 1, but it has imaginary part, right? So the most reasonable guess at this point, right? Both of them, magnitude is 1, alpha is 1, beta is another number, like this. The most reasonable guess is beta equals to I, right? This is a very special point where you have Q and P offset by 90 degrees. Right, so you have them offset by 90 degrees, which make perfect sense because think about the kinetic energy and momentum energy. Okay, their solution, one is sine, one is cosine. If one is sine, the other must be cosine, just like this, sine, cosine. Right, so they're off by 90 degrees naturally. So if you add beta equals I, which is theta equals 90 degrees, okay, this entire thing just makes sense. Okay, and then the next thing is A dagger equals to okay, A dagger equal to this. So this is a guess, and then when we come back, we will verify that, okay, these two are indeed creation and annihilation operator. Now, to verify that whether these two are really annihilation and creation operator, the thing that you wanted to do is to use this equation here, right? So what it tells us is that, okay, if your eigenstate, nth eigenstate, then when you apply Hamiltonian on it, then you always get energy level En, right? So the question would be, if you apply Hamiltonian operator on A, N, okay, would it give you right? So this one, okay, if you give you En minus h bar omega, that means you indeed lower the photon number by 1. Okay, this is a key, the key concept of how to verify that this creation and annihilation operator. And for creation operator, then the thing would be like this. Okay, so the question is, can we verify this? And so one difficulty you will see here is that, okay, if we just plug in A and A dagger here for calculation, then what we're really doing, okay, is that we're again calculating on the function, okay, itself, right? So it's relatively it doesn't make much sense because we try to replace Q and P with another operator, but when we calculate it, if we still use Q and P, then the whole thing is not really doesn't really have a point here, right? Now, one important thing I want to talk about here in quantum mechanics is commutation, right? Because if you look at how we are going to calculate H act on A act on a wave function, right? If you plug in Q and P, then the entire thing is going back to the it's going back to the Schrodinger equation, to the differential equations, right? So instead, one thing we can do in quantum mechanics is that this is discovered by Heisenberg independently from Schrodinger's equation, is that he found out that for position and momentum operator, okay, you always have the commutation which is defined as xp minus px. Okay, and in classical physics, this is 0, right? The position momentum minus momentum times position. Those are just numbers or functions, so they should be 0. But in quantum mechanics, because momentum operator now here is a function, well, it's an operator, and an operator or matrix, right? Operator and matrix, you know that you can't simply switch the order between a function and an operator. Okay, so what we can see here is that if you do, let's say xp on the function f, then we know it's x. Okay, x is just x, and then h bar divided by I partial x fx. Right, this is xp act on the function. But what about px act on the function? Px act on the function, then you have h bar I, and then partial x. And notice that because for any operator, it's always the one that nearest to the function that act on it first, right? So you first have x act on x on fx, or just multiply x to the function fx. Okay, so now notice that, okay, if you do this differential, then there are actually two terms, right? There's a chain rule here. So you have h bar I. First, you act on fx, okay? Then you have x partial x fx. This is exactly the same as this term here, but you have one more term, that is this act on x, right? So it's h I fx, right? If you act on x, then you're left with fx. So xp minus px, act on a function, is this minus that, so give you minus h bar I fx. Okay, and you can multiply I on both, you can remove the minus I from lower to upper, and then it becomes I h bar fx. So that's why we say that, okay, the commutation relationship between these two operators, they're not 0, they are I h bar. And this is, in advanced quantum mechanics, okay, this is actually the key to, this is really just the key to for quantization, because the commutation relation is, you can think of it as, this is the critical difference between classical mechanics and quantum mechanics, right? In classical mechanics, you will never see that two variables, when you switch orders, suddenly their value change. Okay, and also this is linked to Schrodinger. This is linked to Heisenberg uncertainty principle. That if you measure x, with infinite amount of precision, then your momentum would be unknown. Okay, and this is actually in quantum mechanics courses, and we're not going into detail here in our quantum electronics class. Okay, so if we want to calculate this, then one thing we have to do is to not use QP, okay, but only use A and A dagger. And you might wonder, okay, how is that possible? Because Q and P, they have a relationship here, and A is expressed by them. Is there any way that in quantum mechanics you can get rid of Q and P, but then still represent what they mean in the Hamiltonian? And the way to do that is called commutation, which is actually discovered by Heisenberg, okay, independently from Schrodinger. And then later people show that okay, these two different methods are actually the same. So commutation is defined as QP equals to QP minus PQ. Okay, it's like the difference when you change the order. And it's very interesting that if it's position and momentum, then what you will see is not 0, but a number IH bar. Okay, and this is very, very different from classical physics, because in classical physics, no matter what you have, either you have a variable or you have a number, you always, when you switch them, right, they're always equal to each other and you end up with 0, right? But in quantum mechanics, this is not 0, and this actually leads to Heisenberg uncertainty principle. And then in Heisenberg's case, okay, this he used this to develop the matrix form of quantum mechanics, and which is actually equivalent to Schrödinger equation. Now, how can we understand this? How is that possible, you might ask? Okay, and this is actually quite straightforward, because if Q and P are number or function, then you can switch them. But if they're operators, or if they are matrix, right? You guys learned matrix in linear algebra. You switch two matrix, they're not necessarily the same, okay? A and B is not necessarily the same as BA, right? So for here, let's say if QP act on a function f, then what you will have is IH bar Q partial Q FQ, right? That's what you have. And then PQ F would be Q versus act on F, which is Q FQ, right? Just space. And then you have IH bar P act on both of them, right? Then you see that here you have to use the chain rule that you first act on Q and then you act on F. So you have IH bar Q partial Q F. This is the same as this one, plus IH bar if you act on Q and then you left F here. Right? So if you subtract these two, you will find out, okay, it's actually a number multiply F. Right? So this is why the commutation relation is IH bar. Okay, IH bar. And this is very, very important in quantum mechanics. So if you think that the commutation relation here is equivalent to having an operator here, is equivalent, then what we can do is that we don't have to care about what is A and A dagger in terms of their operator, in terms of their differential operators, but we only have to care about their commutation relation, which is A and A dagger. Okay. How do they commute? And the way to calculate this is very straightforward. Okay, it's use this, and then you know how Q and P commute, and then you can get how A and A dagger commute. So let's write it down. Okay, A and A dagger. And then you can neglect all the coefficient, right? Because it's always Q times P. Whenever you see Q, you add this coefficient. Whenever you see P, you add this coefficient. So you you don't have to carry them in the calculation. And this one goes to Q plus IP Q plus minus IP minus Q minus IP Q plus IP. Right, and then you expand it. This one will be Q squared plus II minus 1 plus P squared. Okay, and notice that you can't switch the order. So QP, so minus I QP, and then PQ, right, plus I. In the past, you might want to throw this away, right? But here you cannot do that anymore because these two are are not the same. And then minus, okay, minus q square minus p square minus, well, here's plus, let's see, minus qp, right, minus iqp, and then plus ipq. Right, and then you can cancel all these terms, common term here. And then what you get is, you get 2 minus 2 I qp minus pq. Right, and then now you have to bring the coefficient back, right? Because q always carry this, p always carry that. So you have minus 2i in the front, and then m omega 2h bar times 2m omega h bar. Okay, and then this is qp minus pq, which is just commutation of ih bar, right? So then what you have here is that you can cancel m omega, 2 and 2 canceled here. So equals to minus I, okay, h bar, right? H square come out. And this one is IH, right? This one is IH here. So II is, okay. So we can conclude here is that the commutation relation for A and A dagger is extremely simple. It's 1, which means, okay, our our definition might be correct, because things don't easily go to 1. Okay, there's no such thing as coincident, right? So this is 1. Now what do we do, right? So now what do we do? So the way to do this is instead of using Q and P now, okay, you want to use A and A dagger for all these calculations, and to do that you have to convert H into A and A dagger. So what we can do here is we can write down H, right? If H is A and A dagger, then the entire equation is about A and A dagger. Then you can use commutation relation, okay, to get the number you want. So okay, and you can plug in what is Q and what is P, right? You add those two equations, you get a relation between A and Q, and then you get Q, how expressed with A and A dagger. You minus these two equations, you get P, right? So if you do that, then what you get is that, let me write it down here, equals to m omega square h bar 2m omega a plus a dagger square, okay, plus square, right? And then minus m h bar omega 4m a dagger minus a square, right? The minus sign comes from the I, and then this minus sign comes from this minus that, okay? So and then you will find out, okay, this is equal to 4h bar omega, okay, a plus a dagger square minus a minus square. Okay, so all you need to do is calculate this, okay, using this equation, and it's fairly easy to see that, okay, you have a square plus a dagger square plus And now you can't say 2 dagger, right? Because there's an order here. So it's a dagger plus a dagger a, right? So this is one trap. Okay, in quantum mechanics, when you have a square, you can't just write down a plus b is a squared plus 2ab plus b squared. There's no such thing as this. Okay, and then minus a square minus a dagger square minus a plus, right? Plus, there are two minus a dagger plus a dagger a, right? So if you do this, you cancel all this term, right? And then you combine all this term, then you get 2 h bar omega a dagger a plus a dagger, right? And you can further simplify this, okay, by using this commutation relation where you have a dagger minus a dagger a equals 1. Right, so a dagger equals 1 plus a dagger a. So this gives you Hamiltonian of h bar omega divided by 2, and then okay, this one plus 1, right? So it's 2 a dagger a plus 1 equals to h bar omega a dagger a plus 1/2. Okay, so this is your Hamiltonian expressed in terms of a dagger a. Okay, and if you look at this, this is already very similar to your eigenstate function. There's h bar omega here. There's 1/2 here, and then all the thing you need to do is to show that a dagger a act on psi and give you a number n. Okay. And also you can see that why people use creation and annihilation operator instead of going through the QMP calculation. Now let's summarize what we have just seen. Okay, is the commutation relation is a dagger minus a dagger a equals 1, and then the Hamiltonian can be written as okay, right, so now the only thing that we need to do is to plug in those and calculate this one. Okay, calculate this one. So let's see, h bar a plus psi n. Okay, when we do this, keep in mind that we can use h bar plus psi n equals to en, the wave function itself, right? So then what you will have is you will have h bar omega a dagger a plus 1/2 a plus psi n. Right, you have this, and then you can split this into two parts. Then you have h bar omega, okay, a dagger a plus psi n plus 1/2 a plus psi n. Right, so this part actually is okay, right? Because on the right hand side we need a plus psi n and then a number, right? A plus psi n and a number, and it just gives you this number here. So the thing that we want to change is this one. We want to make it looks like, okay, let's see. We want to make it into a number that we know, right? Currently, we apply a dagger a on this wave function. We actually don't know what it will come up. Okay, so to do that, we have to remind ourselves of this relationship, right? The eigenstate relationship, where you have en okay. And also another thing is that here, when we use this relationship, we're not assuming we know this. Okay, we're not assuming that. We will actually derive this. Okay, here we just assume there's an eigenfunction, eigenstate with an eigenenergy that satisfies this condition, and that's always true. Okay. Then, and what this means is that your h bar omega a dagger a 1/2, okay, act on this wave function, give you En, right? So in another word, a dagger a act on psi n will equal to En minus h bar omega minus 1/2. Okay, so so here, okay, you can see that if you can get a dagger a act on psi n, then you can reduce this to a number. So what it means is that, okay, you have to somehow modify these terms, right? Because right now it's a act on psi n. You want to change it to a dagger a act on psi n. So what you can do is you can say, okay, I know that a dagger a, based on commutation relationship, is a dagger minus 1, right? A dagger minus 1. Then you can plug in this into here. Then h a psi n will equal to h bar omega, which is the same. Okay, a dagger plus 1, right? A dagger plus 1 a psi n, okay, plus 1/2 h bar omega a psi n. Right, and then you see, okay, you get another number here. Let's see. This is minus 1, yes. I was thinking, okay, the number doesn't add up. Okay, minus 1 here, okay, minus 1. Right, so you get another number out here, and you can see that it can combine with the other term, with the last term. So this is minus sign, okay. Now then you can use, okay, the relationship up here, right? Because a dagger act on psi n. This is operator, right? So you have to start from the right side, okay? A first act on this, a dagger act on this, and a act on this, right? So these two act on this, give you this number, right? So then this equal to, so h bar omega times a, and then your En h bar omega minus 1/2, okay, minus 1/2 psi n minus, okay, 1/2 okay. So then you can cancel all this term, and then it's just numbers now. Then what you get is that you have En, okay, a psi n minus, okay, there's 2 h bar omega. So h bar omega, 2 1/2 h bar omega a. Okay, so it's En minus h bar omega a dagger. Okay, so what it tells you is that, okay, a psi n is indeed an eigenfunction of your Hamiltonian, right? Because when you apply a Hamiltonian onto itself, it gives you a number, and the function remains itself, right? So a psi n is indeed still an eigenfunction, and then the eigenvalue is reduced by h bar omega, right? You can calculate the same thing and then show you that we're not going to repeat this calculation here, but you can do the same calculation, and then you will see that, okay, if it's a dagger act on psi n, then you have En plus h bar omega. You have En plus a number. Okay, so yeah, so now if you start from like a En state, then you can generate two more state, which is a dagger psi n, a psi n, right? And then this energy is En minus h bar omega. This energy is En plus h bar omega, right? And then you can keep doing this, act another annihilation operator to generate one order lower, and then one order lower, and keep going until you hit the ground state. And then we call the ground state psi knob. Okay, psi 0, ground state. So for the ground state, it's interesting, right? For the ground state, first of all, when we calculate this relationship, when Hamiltonian act on this, give you eigenenergy minus a number, right? We didn't say that this can be eigenstate. This can be ground state. So in fact, for ground state, you also have this relationship. Ground state energy minus h bar omega. Okay, so you might wonder, okay, if this is the case, then how is this ground state, right? There's another state that has slightly lower, has h bar omega lower energy than your ground state, so it's not a ground state. Okay, so the key here, the argument is that, okay, assume that this is really the ground state. Is there any way that you can satisfy this equation, right? Is there any way you can avoid violating this equation, because this equation is accurate according to all our calculation? So the trick here is that, okay, to avoid having another state and to avoid violating this equation, then you can always let a psi knob go to 0, right? If this is 0, then there's no state there, right? If there's 0, and then this number, okay, really doesn't make much sense. It's something act on 0 equals something times 0. Then this thing can be arbitrary, right? So this is a ground state condition, okay? A act on psi knob go to 0. And then we know what A is, right? A is Q, P. P is differential of Q, right? So if you use this, you can actually, A as a function of P and Q, act on psi knob as a function of Q equal to 0. You can actually get a differential equation, and you can solve what psi knob is, and then we have that in the note. Okay. Now finally, let's get all the energy level, okay, and then wrap up this class. And then in the next class, we'll talk about what this ground state really means, and then how to use all this creation annihilation operator to create nonlinear optics calculations. Okay, so one important thing here we learned is A act on psi knob equals 0. Now if you calculate the eigenenergy of this state of the ground state, then what you would do is you would have Hamiltonian act on it, right? Hamiltonian act on it, give you a number of and your operator, give you your number and your state, right? So we have h bar omega a dagger A plus 1/2 act on psi knob. Okay, so the first one is that, okay, 1/2 h bar omega is just a number, right? So that's fine. And when you have this act on here, then what you see is that the A has to first act on psi knob, which is 0, right? So this entire operator, this thing, goes to 0 when you act on the ground state. So this thing goes to h bar divided by 2 psi naught, right? So E naught equals 2 h bar omega. Okay, so if you go back, right, when you go back one state, right, A dagger act on psi naught. Let's say here, A dagger act on psi naught. The eigenenergy would be E0, E naught, right, plus h bar omega. So this one would be, the energy would be h bar omega plus 1/2 h bar omega, right? And then you can keep going up, going up, going up by adding the A dagger. And then eventually, okay, eventually what we will have is En equals to h bar omega n plus 1/2, right? So, and n start from 0, 1, 2, okay. And this really, okay, we'll say it's a linear algebra way, okay, to get your eigenenergy without going through the differential equations. And if you want to know what is the eigenfunction, right, then what you can do is say, okay, we said it before, you can solve this equation because this is a differential equation. You can actually solve it by plugging P and Q, okay? And after solving that, and the next function, for example, the first excited state, then what you do is you apply A dagger on psi naught, right? Because you already know what psi 0 is, and then A dagger is just Q and P again. Okay, you act on it, and then you act on it, and that's how you get the Hermite polynomial. Okay, and I'm not sure if it's already an hour and 15 minutes, but I'm a little tired today, so we'll stop here, and then in next week we'll start to talk about how to use these operators to do something interesting.